having server issues with ResponseWare. We'll see how that goes later. Okay, energy. More on energy today. Any questions you guys have come across in your studies or observations? Yes, I heard there was a tornado. Yeah. It was like 100 feet wide or something, so it wasn't real wide, but it did some damage. Okay, then. We had introduced a few new terms. Work being a force times a distance. That tells us, guides our thinking. The equations are relationships. The similar one was, impulse was force for a certain amount of time. Each of those brought about changes. Impulse, a force over time, brought about a change in what? Good, I hope you got that one by now. Momentum. That brings about a change in momentum, which can change its mass or its velocity. Work brings about a change. A change in what? Work is a force times a distance, so you apply a force for... This could be the same thing too, you're interacting with something. It takes a certain amount of time, you change its momentum, but you have to act over a certain distance. And that brings about a change of what? It can change your position, yes, good, I accept that. What else could it change? Energy is generic there, so that brings about a change in kinetic energy, which is the energy associated with movement. Good, motion. It's also a change in gravitational potential energy, which was the change in relative to position, which is based on position. Kinetic energy was 1/2 mv squared, and gravitational potential energy is mgh. So work can bring about a change. Brings about a change in energy. It transfers energy from, say, kinetic to potential, or vice versa. So you can think of it as, moving something. And if you say it that way, moving something, change of velocity or position. You can do work on something. When you exert a force, I exert a force on the object. Thus it changes its energy, or can. Okay, I just thought of a question. If you double the speed, what did you just do to the kinetic energy? You quadrupled it. If you triple the speed? Right. How do you slow yourself down if you're cruising along the highway? You hit the brakes. There's a force now acting for the braking distance. You're doing work, the work done by the friction of the brakes, and that changes your kinetic energy from something to something less. Hopefully, zero if you're trying to stop. Think about that then. If you're going 50 miles an hour and you slam on the brakes, it takes a certain distance to stop, doesn't it? So quiz time. What if you double your speed? You're now going 100 miles an hour. How long is it going to take to stop? 4 times the distance. People overlook that. You're not sitting there processing the physics in your head when you're driving, right? I'm not naive enough to realize that's probably not what you're thinking about. But you should be, especially if it's adverse conditions, like a wet road, like today, or icy. If you go faster, even just a little bit faster, It doesn't take just a little bit longer to stop yourself. It takes the power of 2 longer to stop you. With that obvious example, from 50 miles an hour, it takes a certain amount of distance, to 100 miles an hour, it'll take 4 times the distance. If you have kinetic energy going 50 miles an hour, 1/2 mv squared, and you come to a stop by braking, where did that energy go? It was transferred to heat. So could you tell me how much work was done? You know, somebody asked you, by braking, how much work did you do by braking? Do you know the force? No. You might not even know the distance. You'd have to go out there and measure how far it took them to brake, right? But in terms of energy, you don't need those grimy details. That kinetic energy before the collision, right? You look at your total energy. We'll write it like this. Total energy before equals total after. Just like total momentum's conserved, total energy is always conserved. You can't create or destroy energy. So if you're in a car, you have kinetic energy, right? Do you have potential energy? You guys don't sound confident yet. Yeah, you're moving at 50 miles an hour down the highway. Do you have gravitational potential energy? Not relative to the road. That one's always, since it's the energy associated with position, it's always relative to something. So there's always a disclaimer there. Well, relative to what? Well, we usually think the ground is 0. So it can't fall, in other words. It doesn't fall anywhere. So initially, it doesn't have any gravitational potential, but it does have kinetic. What do you have after you finish braking? Gravitational potential energy? Did you gain height? Yeah, you didn't change your height. You didn't exert a force of its weight to lift it or lower it. So yeah, you didn't change the gravitational potential. Let me write. So that's still 0. You didn't change that. Do you have kinetic energy now? No, you stopped moving, so that goes to 0. Is this equation balanced? No, what are we missing? Where did this energy go? You just told me a moment ago. Heat plus heat. And where'd that heat come from? The work done by friction. So if somebody were asking you, how much work was done by your brakes? You don't have to know all that nitty-gritty of forces and distances. If you knew how fast you were going in the first place, you know your kinetic energy initially, and you know it all went to that. So you started with that much energy, and you ended up with that much energy. It went somewhere. Those have to be equal, right? Yes, no, maybe so. That's the conservation of energy game. Let's give another example. Loop-de-loops. We'll try the big ball here. Roller coasters. Who likes to go to the amusement park here in Lagoon? Yeah. Hey, not Lagoon? Where do you go? Disneyland? Go to California? What, do you know why people like generally, I'm stereotyping, but it's generally true. Why people like amusement parks? What? Adrenaline. Good. I'll agree with that. And what gives you the adrenaline? The G-force, he says. What's a G-force? Yeah, it's the earth pulling on you, And we've learned that Earth pulls on you and causes you to accelerate. Do you guys like going fast on the roller coasters? Is that the G-force? Yeah, not everybody does. That's either why you like it or why you hate it. But is it speed that provides the G-force? G. G. I like that you're saying G. It stands for gravity. We usually plug it in our equations. What's it represent? We call it gravity. But is that a force or an acceleration? Yeah, it's an acceleration. Newton's second law. And we replace the A with G. There's that G force. That's what gives the force. But yeah, technically that's an acceleration. That's why most people like or hate amusement park rides. It's not how fast you're going. It's not speed. You go fast on an airplane, several hundred miles an hour, right? Do you notice it most of the time? No, unless you hit turbulence or something. But you know what turbulence does? It changes your velocity. It accelerates you. That's when you feel it. You know, you're in your car going 100 miles an hour. You think nothing of it. You toss the ball up. You talk with your friends. You're paying attention to the road. And no big deal. It's when you have to brake or turn or accelerate. That's why people like amusement park rides. It's the acceleration, not the speed, the acceleration. I like pointing that out. That's when we feel it. So you can calculate all those accelerations and changes in velocity. You can also play the conservation of energy game. How fast do you need to be going on a roller coaster so that you don't come off the track here, right? You don't want to fall off here. You're right here. You know, if you're not moving, you fall. You got to be moving there. You need some kinetic energy. How much energy do you need? A lot. You're moving in that direction, so you have kinetic energy. What else do you have at this point? Gravitational potential energy relative to the ground, we'll say. What energy do you have here? Yeah, it's just kinetic. What energy do you have up here before you start? Potential. How about here? Both. What do you think the total energy equals at the different places? The same. Exactly. So if you want to know, and engineers have to do this, how high up do we need to start? That's what they do. You know, they strap you in. That's the boring part of the ride where you're climbing up, because they're doing work on you to gain gravitational potential energy, so you have enough energy to start with, so that you have this enough here. Let's look at it. Something like that. So if you start over here at H, you have gravitational potential energy of mgh. And I'll say you did work in the first place to get that, to get up there at point A. Let's say this is D, distance D. Actually, we'll make it easier. Well, yeah, D works for diameter. Diameter of the circle. How much potential energy do you have here at point B? How much gravitational potential energy would you have at point B? mg d, because you're that high up. You came down a little, so you gave up some energy. How much potential energy do you have here at point C? mgh, but h is 0. Yeah, so you have no height. You have no gravitational potential there. How much kinetic energy do you have here? Bingo. That has to equal the H that you started with, right? The mgh you started with. Because it's now all in the form of kinetic energy. So I could ask you, how fast are you going? Watch this. If mgh is what you started with, and it turns into 1/2 mv squared, could you solve for velocity? All you need to know is how high up you were to start with. Do you see that the mass doesn't even matter? It cancels on both sides. You take the square root of both sides, well, multiply the 2 over. Anyway, given the height, how high up you start, you could know how fast you're going at the bottom. So right here, if I lift it up here, let's say I lifted a meter up. That's not a meter, but it makes our math easier, right? Boom, right there. Well, let's see. 2 times, we'll call it 10 meters per second for 1 meter. That's the square root of 20, which is, I don't know, 4 squared is 16, 5 squared is 25, so it's somewhere in the middle. 4 to 5 meters per second. You know how fast it's going, right there at the bottom. Yeah.
Why is the back of the roller coaster faster than the front?
Ooh, good question. Why is the back of a roller coaster faster than the front? You got any ideas? Here's the roller coaster now. Okay, we're going to start. Have any ideas? She says if you're sitting back here, you might be going faster down here than if you're sitting here. You started up higher. I mean, in this example, up here has more gravitational potential energy than down here. So when you start falling, when the front gets down there, it didn't start from as high up. So it doesn't have as much energy here. The velocity is less. There's other things going on, but does that help? Great question. Do you have kinetic energy here at B? I hope so, or you're going to fall. So this total has to now equal. You started with the energy at A, and that has to be the energy at B. The energy at A was all potential. The energy at B is potential plus kinetic. If you know those two heights, or the difference in the height, you know how fast you must be going to clear the loop. And that's the kind of game engineers have to play to make these safe. Let's see. Do you think it'll clear from here? Oh, no. So I need a little more energy. Oh. Let's go a little lower. If you listen, you can tell it comes off the track. So if I was an engineer, that wouldn't be real safe, would it? So, go a little higher. Also, real life comes into play, doesn't it? They try to minimize friction. But some of this gravitational potential energy converts to friction. Heat, the work done by friction. So you have to go even higher. That would be easy, though. They just do this, plus the work done by friction. You start with this much. Where does it go? Here, here, and here. So if there's some minimum speed, to clear it, you're going to have to start with more. Some of it's going to go there in real life. But it's just conservation of energy. And it makes solving things a lot easier. You don't have to figure out the forces and the distances and the velocities and whatnot. You can just get from point A to point B to point C. I think this would be a good one to do now. You got any questions? All right, I call this high road, low road. This is the high road up here, stays up top, and the low road where it goes down here. If I start them at the same height, they'll start with the same amount of energy. I'll just hold them. And I want to pose the question. They'll roll down. Whoop, maybe I should, so I ensure that I let go of them at the same time. And line them up. There we go, that's better. So they'll start at the same height. They'll come to the flat section. And then they start diverging. Who will get to the end first? High road, low road, or the same? So if you think the same, high road, low road. All right, most people think it'll be a tie and next the high. So the fewest of you think the low road will win. Why do you think they'll tie? Who would like to tell me why they think it'll tie? Any brave souls? Yes?
As it goes down the low road,
It
gains kinetic energy.
It gains kinetic energy here.
As it goes up, it loses the same amount of kinetic energy.
But it loses kinetic as it comes back up.
Gains gravitational potential energy, same amount, so that's equal to
It's also losing gravitational potential at the same time the kinetics increased. But then over here the reverse happens. So it's a washout and they'll tie. That's logical. Any other thoughts? Oh, go ahead. They're going at constant velocities the whole time? Okay. Because I let it go at the same time? Okay. Lose some going down. No, it gains kinetic energy down. It does lose the kinetic as it goes back up. Why would it lose less here than it gains here? It's harder to go up than down? All right, it's good intuition behind you. Friction here on the straight spot would slow it down more. Would it slow it down any more on this straight spot than it would in this straight spot? No, this is fine. We're just getting ideas out there. Yes? You think the top will finish first? Because this one has to cover a longer distance. Interestingly, these started out the same length. I cut them the same length and then I bent this one. Shall we just do it? All right, drum roll. The low roads, the minority have it. Which means most of us are confused. Let's do that again. So can you see they're going about the same speed to this point. Watch it up to there. Watch it to here. And then, as you said though, correctly, this one gains speed. So the velocity isn't always constant for this one because it gained kinetic energy as it lost potential energy. So this one got going faster. It got ahead of it. Now we saw over here, and we know, you said correctly, this gains potential energy, thus losing kinetic energy, and it slows back down. Yet it's still 1. Why? What's that? At that point, it's too far ahead. There's truth to that. Didn't slow down as it comes up the hill, kind of like he said over here. Somehow the energy change here is not exactly the same energy change here, so it doesn't get up to the same speed it started with. Let's try this, if I can do it. This one's slower, so I'm going to give it a head start. And then I'll release the low road. So that when they get here, I'll try to get them to get here at the same time. We can compare their speeds on this section of track. Might take me a few. Let's see here. So I need to start him first. Now. Try it slightly again. Wasn't wonderful. Let me see. Okay, this isn't perfectly level. That shouldn't be going backwards if it's not level. Let's just start up higher. Try that. Okay, release it sooner. Now that we're going faster. That was better. Repeat. Can you compare now? One more time. They should be the same. Oh. Yeah, they have the same velocity here. Let's look at it in terms of conservation of energy. They started with the same amount of potential energy, right? They've both lost the same amount of potential and both gained the same, so they're going the same speed here. This one loses, regains. Yes, there's friction here, but there's the same amount of friction here. So when they end up at the same height, they have the same gravitational potential energy. Thus, they must also have the same kinetic energy, because the total has to stay the same, right? So they're going the same speed by the time they get up to here. It's just that the high road gets there later. Because if this one is gaining kinetic energy, it's going faster. And you cover more distance in less time. It gets ahead. So for this section of the trip, the low road was always going faster than the high road. As soon as it starts going down, it's now going faster. Faster, faster, faster. Constant, but it's still faster. It slows back down, but even right here, it's still going faster than this one until they get up to the same height, and then they're going the same speed. So it just got ahead. Fun, huh? We got to do it again. You can kind of see too, once the low road gets up here, the high road's still up here, but you can see the speeds are about the same that way also. So I guess even one more time. Right now. Questions? Does it make sense now? So that, yes, Court.
So then the impulse would be greater on the low road than the high road?
I'm sorry, because I was coughing, I didn't hear you.
So the impulse would be greater on the low road than the high road because there's more time?
The impulse would be greater on the low road than the high road. Impulse is a change in momentum, and if it had a greater change in velocity, because it had a correspondingly greater change in kinetic energy? Absolutely. Look at it this way. Earth pulled on it with a force and pulled it down. Force pulled it down. Over a certain amount of time, that caused a change in momentum at the same time that it caused a change in kinetic energy.
You also say that its net acceleration was greater than the other one on top, so that's why it ended up sooner.
Its net acceleration was greater than the one on top. Right, which is why it got going faster. Yep. All right. Who still doesn't trust physics? Be honest. This stuff still seems kind of magical, and I get it when you say it, Adam, in class. I'll trust you as my physics teacher, but when I'm on my own in real life, I still worry. I wonder. Raise your hand if you're like that. All right, in the red, will you help me today then? Come on down. I'd like to help convince you a little more. So out of all that mumbo jumbo I just said, do you trust me at least?
Yes.
Okay, good. Then I won't hurt you, okay? I'd like you to stand over here, up here. All right. Yeah, this is an actual bowling ball. Yeah, and keep your hands on this side. What we're going to ask you to do is raise that up and hold it right next to your eyes, so it's touching. Stand up straight. Yeah, put your head up. Yeah, and bring your hands up to there. Okay. What I'm going to ask you to do is just, not yet, let go of the ball. Okay. We know what it's going to do. It's going to swing and come right back. Your task is you can't move. Even when it comes back, you can't move.
You're going to hit me?
Do you think it'll hit you?
No, I trust you.
How much potential energy does it have right now? MGH. How much will it have when it comes back? Can it have more? No. Where would the energy have come from? So go ahead and lift it up. I'll make sure you're not moving. And just let go. Open your eyes. This is fun. Whoop. Thank you. See, you can trust physics. The laws of physics don't fail us. So yeah, here, MGH. What's it convert into? Yeah, it still has less potential, more kinetic. All kinetic, no potential. More potential, less kinetic. All potential again. The same amount we started with. Now, you guys are good scientists, and you probably noticed it'll never come up higher and hit you, but it actually was a little less. Did you see that? Let's try it again. Watch it. I'm trying not to hit you there. And, whoa, okay. It's a little less. Why? Air resistance and the friction up there do work on it and convert some of this potential and kinetic energy to heat. So it doesn't have quite as much potential when it comes back as it started with. But it'll never have more unless, you have somebody that unintentionally pushes it. I've seen that. That's why we do this. If people are like this, sometimes they use their little fingers and add energy to the system. Then it could. All right. Let's do this one. Here's my ball chain of science. You know this one? I just went to the hardware store and bought this. It's all connected. I'm going to take it and just drop it over the edge. When you drop things, you know what happens, right? Gravity accelerates them down and they fall. It's going to pick up what energy? Kinetic, and lose gravitational potential. All right, it'll fall straight down. Ready? Magic. All right, everybody usually wants me to do it again. It takes me a minute to refill it. The only trick is you can't wad it up and stick it in or it doesn't come out smoothly. So talk to your neighbor, why in the world did it go up before it fell while I refill? Whew, okay. What's your thoughts? It's magic. Well, see, that's why I like physics. Another reason. Some things can seem magical. Magicians need skill. Sleight of hand and misdirection. Physics, I don't need any skill. These are the laws of nature. All I have to do is just understand them, and they do it for me. I don't even have to try. I'm not tricking you at all. So. All right, how about a more physics answer? Thoughts? If the chain's going up, what's it gaining? Potential energy. Awesome. And if it's doing that, what else is happening at the same time? It's losing kinetic. As it falls, you know it's gaining kinetic and losing potential. Well, I don't expect you to realize, but you could do it at high speed video, or it doesn't even have to be that high speed, and video analyze it. As it falls, you're right, it picks up kinetic energy, but not for the whole fall. At some point, it's kind of like a terminal velocity. The weight of it down is balanced by the rest of the chain pulling back up on it because it's connected. And it doesn't go any faster. It just falls at the same speed. It gets up to a certain speed and then falls at that speed. So it's not gaining kinetic. You with me? If it's not gaining kinetic, but it's still falling. So it's still losing what? Potential. Where's that energy going? It's not going into kinetic. It's going in up here to lift it up. So again, because it's connected, the rest of the chain kind of exerts an upward force to keep it from falling any faster. Yet it still loses potential energy, and it's revealed up here. Ready? And maybe we'll do it on this side. Oh, that one's better. Another way to think of it, momentum. How many of you can turn on a dime when you're going fast? Yeah, you can't. Because you have momentum. You have energy also. So think of it. Before the chain can get out of the cup to fall down, it has to go up. The faster that chain falls, the more it pulls on the rest of the chain, and it yanks it up. So it's moving up. It's got upward momentum. Well, it can't just turn on a dime and go, it kind of goes up, slows down, stops, and then accelerates back down. So that agrees with what we just saw. Okay. Let's end with two simple machines. Yeah.
If you were taller and it fell farther so that the chain that's coming down would continue to accelerate, I assume, because it stops accelerating once it hits the floor, right?
It stops accelerating above the floor because at some point it never goes faster.
But if you were up taller, would the arc above the glass increase?
What do you think?
Yes.
Your gut's correct. That's a thinking man's question. I got a ladder out once, put it on here, and stood on top of that. If I got up higher and started with more potential energy, it would fall, but at some point it would stop accelerating. But it has further to fall, so there'd be even more energy going up here, and it would lift up even higher. That's one reason I stood on the table, not just so you could see it better. It looks cooler on the table than it does from the floor. It looks even cooler from a ladder on the table. Great question. Let's scooch this for a moment. All right, here's my 26-pound lead brick. I'm going to exert a force on it to lift it up. Simple machines can help redirect the forces, like pulleys. You pull on one side, and it lifts over here. A lever can do that. All simple machines kind of have that effect. So I'm going to push down over here, but you know it'll have an effect of exerting a force over here. Okay, maybe I will. Jeez. There. There we go. So, that didn't seem to help me in this case. Simple machines can work either way. To give you a mechanical advantage, with a lever you can move where the fulcrum is, the pivot. Now, heck, I can do it with my pinky. And if you think I was faking, you guys can come try it out afterwards. So, simple machines can, one thing that what they can do is they can help amplify your force. So I can exert a certain force, and that's enough to lift a 26-pound brick. But if I do it this way, that's hard. I can't do it very well. So they can help you with force. Now we know energy is conserved. We did this last time. Do it again. Energy is conserved. So in both cases, I'm exerting the exact same amount of work. So I can do a little force over a big distance, or a lot of force over a little distance. And check how far it moves. Over here where I exert a little force, look how far I have to move. That distance. This doesn't end up moving very far, does it? That moves less than I move. But the work is the same. Here's another example. I need 3 volunteers. 1. 2. 3. Thank you. Come on down. Let's see. Let's have... Whoops. That'll be fun for me to untangle later. All right. All right. Carl, you want to take this in? Well, how about you? Whoa! You take this end. Once he takes this one, then you guys can hold it. I'll get out of your way. Jordan, why don't you grab here? All right, now you can lift it up. All right, this is a pulley, block and tackle. It goes around 7 times. Okay, your guys' job is to keep these separated. Okay? Don't let you guys come together. Jordan, your job is to pull as hard as you can to try to pull them together when you guys are ready. And yeah, just here, walk back. You're going to run out of room, so you can just do this. Come on, you guys. This is a piece of cake. Come on. Oh. Oh. All right, you get the point. Thank you. Set it up here so it doesn't slide off, and I appreciate it. Thank you, Jordan. You can just drop it. So another simple machine. Force is involved. Who obviously was trying to apply more force? Who did it look like was having a tougher time? The guys in this case. And it looked easy, relatively, for Jordan. So just like with the lever, you can amplify force. She, because it goes around 7 times, it actually worked out that she could exert 7 times less force than they were trying to. But who moved further? Where did the rope get moved the most? She had to move 7 times as much rope. So less force, but over more distance to keep the work done the same on each cases, because total energy is conserved. One more concept, because I forgot it. Power. It's the rate at which you use energy. Use energy. So power is energy per time. Power. You've heard it. It's measured in watts. A what? A watt. Basically, we hear power all the time. So if you had a 100-watt light bulb, that means you're using 100 joules of energy every second. So it's the rate that you use energy. And my last example, I can walk up the steps, force over height. I now have gravitational potential energy. I just did energy. It took a certain amount of time, so I exerted a certain power. It's just energy divided by time. So what happens if I do it faster? How much more energy did I gain? Same amount. I'm the same height. But did I use more power? Absolutely. That's the idea behind power. It's really all I want you to know about it anyway. So does that make sense? All right. You guys have a great weekend.